time we discussed Pedersen commitments. I never quite know how to pronounce it. So this is a commitment scheme that lets someone commit to like a single field element, and the commitment to the field element is a group element, and the commitment is hiding. So basically, no matter what the committed value is inside of it, the random element. It's assuming hardness of discrete log. So roughly what that means is that anyone who knows how to open a Pedersen commitment to different values must know a discrete logarithm relationship between two where you just like randomly chose group elements and like it's also homomorphic, okay, which means I can give you two commitments, say a commitment to A, some value A, and a commitment to some value B, and without you knowing A or B at all, you on your own can compute a commitment to their sum. Okay, that's what homomorphic commitments are, and so commitment schemes that use cryptographic groups, they all tend to be homomorphic, and in particular, the commitment to A plus B in the Pedersen case is just the group product, if it's a multiplicative group, of the two individual commitments, right? So by multiplying the two commitments together, I get a commitment to the sum of the two values inside each of them. And then we also saw some simple zero knowledge proofs of knowledge for statements about values inside Pedersen commitments. So like, I can send you a Pedersen commitment to some value and prove to you that I know how to open the commitment without actually opening it. In fact, without leaking any information at all about the value I know how to open it to. And building on these sorts of zero knowledge proofs of knowledge for values inside Pedersen commitments, we saw our first zero knowledge argument for circuit sat, and the rough idea there was the prover winds up committing to the value of every gate in the circuit. Or really, it only needs to commit to the values of the multiplication gates because addition gates are just handled via homomorphism. And it winds up, proving that the value inside each commitment actually respects the gate operation. So if you have three gates, like a multiplication gate, which is multiplying, the values computed by two other gates, the prover winds up committing to a value for each of these gates, and then proving using one of these zero knowledge proofs of knowledge that indeed the value inside this commitment is the product of the two values inside these two commitments. And so it sort of, just commits to the value of every gate, and then proves that all the committed values kind of respect the gate operations. And then finally, it only has to open up the committed value for the output gate, to confirm that the circuit really does output the claimed value on the input, which itself is probably also committed. So that's a complete recap of what we discussed last time. Okay. Anyone want to ask any questions about that? Nope. Okay. Then I will continue. Okay, so today I'm going to discuss how you use sort of generalized Pedersen commitment to commit to large vectors instead of just a single value. And so whereas Pedersen commitments themselves, where the commitment is one group element, and that group element is committing to just a single value, a single field element, Pedersen vector commitments are compressing. right? So they will take, n field elements, think n might be a million or a billion, and the commitment to all a million or billion field elements is also just a single group element. So it's like you're, shoving an entire vector inside a single group element. And so it's very compressing. The commitment is much smaller than the actual, vector that is committed. And then polynomial commitment schemes, they like all of them work basically by applying a vector commitment to the vector of coefficients of the polynomial. So we're going to start, discussing various polynomial commitments. And today we'll cover a particularly simple one called Hyrax. And that's probably all I'll discuss. But I might say a little bit about bullet proofs, also known as IPA, which is short for inner product argument. But most likely this will be the topic of next time. And then after that, we'll cover, so next time will probably be bullet proofs. And then after that, probably KZG commitments. And then maybe Dory. Okay. So that's the plan for today and the following sessions. And then after that, we'll move away from groups and we'll discuss hashing-based commitments like Fry and Laharo and breakdown and stuff. So these use hashing instead of cryptographic groups. Okay. Any questions about that?
The question about schedule. Would you say this next times will be after New Year or not?
Yeah. So I think we'll probably do one more week. Yeah, one more week before the holidays. So I guess try to just get through bulletproofs would be the plan. And then so everything else, which I'll put in a different color here, this would be in the new year, I would think.
That sounds awesome. Thank you.
Yeah. Great. Yeah. And then so we, all smart. Well, let me think. Right. And then, probably after that, we still have to cover growth 16, as well as snark recursion and folding schemes like Nova. I'm also working on some new memory checking arguments, like lookup arguments and stuff. So we did one session on lookup arguments. I wasn't thrilled with how it went, and now I'm working on some new ones, which I think are easier to explain. So I'll probably do a session on that before we wrap up. But this is broadly all of the topics kind of left to cover. So I don't know, speculating we might wrap up by end of March, maybe something like that. That would be my guess right now. Yeah. Any other questions about future plans? All right. Okay, so let's dive into Pedersen vector commitments. So here, if I want to be able to commit to a vector of n field elements, okay, there's going to be a commitment key of n group elements, say G1 to Gn. Okay, and I think we discussed this last time in response to a question. Exactly how these group elements are generated depends on context, I guess. So, right now we're just talking about Pedersen vector commitments, but as I mentioned, like all of the curve-based commitment schemes, the commitment itself, all of the curve-based polynomial commitments, you're just applying a Pedersen vector commitment to a coefficient vector. Okay, and so different polynomial commitment schemes will choose these group elements, the commitment key for the Pedersen vector commitment in different ways. So in like Hyrax or really anything transparent. So Hyrax, bulletproofs, Dory, these would just be random group elements. right? So you would in practice generate them by applying like a cryptographic PRG to some predetermined seed string or something. But with KZG commitments and analogs of it, these would be come from a trusted setup. Typically, this would be a powers of tau setup, trusted setup. But right now, let's just say these are some group elements. Okay, and so the commitment to a vector, I guess let's call it U, which has n field elements in it. So U1 to UN in field to the n is just going to be the following. And let's call this a multiplicative group. For now, actually, once we get to bulletproofs, I'm going to switch to additive group notation for reasons that will become clear then. But for now, this is a multiplicative group. So the commitment to U is just a group product. Yeah, so this is the group product here, the group operation of GI to the UI. Yeah, that's it. So it's like, so if you just look at one term in this product, GI to the UI, that you can think of as like an unblinded Pedersen commitment to UI. Remember, Pedersen commitments, the committed value gets stuck in the exponent of some group element. And then, if we wanted it to be perfectly hiding, we would also have a blinding factor. And here there's just no blinding factor. So what we have is an unblinded Pedersen commitment to each entry of the vector. That gives you, if you cover up the product here for a moment, you just look at GI to the UI. That gives you, one group element per entry of the vector. That would be a non-compressing thing. I turned n field elements into n group elements, so I didn't make anything any smaller. But then we product everything together, and that kind of, munges all n group elements into a single group element. Okay, and so this operation, I'll put it in red here. This, product over, all I of GI to the UI. This is called an MSM. For multi-scalar multiplication, also known as a multi-exponentiation. Okay, and that's the commitment. And so, so I guess all I want to right now, all I'll say is, if no one knows any discrete log relations between the entries of the commitment key, between GIs, this is a binding commitment. Okay, so that is, if I give you a Pedersen vector commitment, anyone who knows how to open that commitment to two different vectors must know some non-trivial discrete log relationship between some of these GIs. So that is, I'm not going to go through the whole analysis because it's very similar to showing that Pedersen commitments themselves are binding. But basically, there's some GI and GJ in the commitment key such that the person who knows how to open the commitment to two different values must also know like an X such that GI to the X equals GJ. So that is that's what I mean by discrete log relationship. So it basically anyone able to break binding in the commitment scheme must know like the discrete log of some GI to base GJ for some J does not equal I. Okay, so basically, if you can't compute discrete logs involving any element of the commitment key, then you can't break binding of this commitment scheme. Okay, so that's Pedersen vector commitments, and they're binding. Now, if you wanted it to be perfectly hiding, you could add a blinding factor. So you would take the this unblinded vector commitment, and you would just the committer would pick a random exponent r. We would also add just one more group element to the commitment key. I would call it h, and multiply the unblinded commitment by h to the r. And this ensures that no matter what the committed vector is, the actual commitment is a random group element independent of the vector. So exactly the same as for a standard Pedersen commitment. But the way I like to design ZK snarks is to first design a non-ZK snark, only worry about succinctness, not ZK, and then later find a way to add ZK in. And so I'm not going to worry about these blinding factors further. But as we've discussed before, there's typically two different ways you can make a non-ZK snark ZK. One is to just use composition, meaning use a ZK snark to prove the non-ZK snark proof. In that, if you go that route, you don't have to worry about the blinding factors or anything. Just non-ZK is enough because you're going to get ZK later through composition. The other route is to directly make things ZK without composition, and then you would need to bring in these blinding factors. These blinding factors ensure that when I commit to a vector, the commitment itself leaks no information about the vector. So I'm just mentioning you can actually make this a hiding commitment, but I'm not going to worry about that. Okay, questions? Yeah, they should be. I think normally in elliptic curve groups, in practice, um, they're typically, large. They're groups of large prime order, and so any group element in the cryptographic group is in fact a generator of the group. Um, so yes, yes, but also like typically it's trivially always the case. um, so yeah, so these are all generators of the group, but also like any group element, is typically going to be a generator of the group. So I personally I just think of these as random group elements, and all of which are guaranteed to be generators. Does that answer the question? Okay, great. Okay. Yeah, so let's briefly talk about how expensive it is to compute this commitment. Okay, so if you do it naively, what you'll do is you'll just directly compute GI to the UI for each I, and then product them all together. Okay, so that naive algorithm, I'll call it the naive MSM algorithm. That costs n exponentiations, which in additive group notation are called scalar multiplications. And that's really slow because each exponentiation in one of these groups, like these exponents, can be as big as 2 to the 256 or something, right? So like raising a GI to the power 2 to the 256, that actually requires 256 squarings. So this is some, if you did it the naive way, this would be like each exponentiation would be several hundred group operations. So actually it turns into something like 400 group operations. By group operation, I mean like, if we're calling it a multiplicative group, I mean group multiplication. So this would be super slow. This would be like 400 times n group operations. And each group operation in turn is roughly equivalent in work to six multiplications over what's called the base field of the elliptic curve group. Okay, so in terms of I like to express every I think of field operations as like the simplest operation that snark provers tend to do, and so a naive implementation of a Pedersen vector commitment is actually equivalent to like 2400 times n field multiplications. Okay, and then this is slow. Yeah, you for every value you're committing to, you're doing 2,400 field multiplications. Like, that's not great. But there's a better than naive algorithm for this called Pippinger's algorithm. So Pippinger's MSM algorithm. And I'm not going to explain how it works. So I'm just going to assert its costs, which is it speeds up the naive algorithm by a factor of about log n. Okay. And so, like, rather than being, 2,400n field multiplications for the naive algorithm, this will fall to, like n is often like 2 to the 20 or something. So, 2,400 n over log n, is starting to look more like, what would that be? Like 100 n. Okay, so like that's a major speed up in practice. Like in practice, this is like a 20x speed up over the naive algorithm. So definitely worth being aware of. I think if you are new to snark design, you don't know about Pippinger's algorithm until someone tells you about it, and it's really important, right? Like this is an order of magnitude, for the prover time. It's critical. Another thing I want to mention is another sort of wrinkle in terms of commit time, in understanding how expensive it is to compute these commitments. Okay, small values are much faster to commit to than big values. Okay, and what's going on is if I want to, so here's the commitment, remember, GI to the UI. Okay, now, like some quick like intuition or just maybe just a fact, say, I know that all UI are in 0, 1. So, they live in this giant field, but they're all in this tiny, tiny, tiny subset of the field. Right, these fields that come up with elliptic curve groups, they're always at least 256 bits. And so, these are using just one out of the 256 bits, specifying each field element or something. Okay, now, GI to the 0 is just 1. In other words, zeros are literally free to commit to. and GI to the 1 is just GI. And so, I said that an exponentiation in general, if the UI is like an arbitrary exponent, I said that would be like 400 group ops. Okay. But for arbitrary UI, like if it's like a random exponent or something. But if I know that all the exponents are in 0, 1, 400 group ops turns into like less than one group op, right? It's like ones cost one group op rather than 400, and zeros cost 0 group ops. Okay. And so in general, it's not just zeros and ones that are fast to commit to. In general, with these MSMs, small values are much faster to commit to than big values, right? So like if each UI is in 0, 1 up to, say, I don't know, 2 to the 16 or something, then it will still be the case that computing this MSM can be done with about one group op per UI. So long as n is at least about 2 to the 16 or so, let's say 2 to the 20 equals a million, for just to be conservative here. So in summary, let me just summarize this. If you're committing to like random field elements and you do it really naively, you don't even use Pippingers, it's 2,400 or so field operations per committed value. Okay, if you use Pippingers, which of course you should do, but you're committing to random elements, you're still talking about like 100 field multiplications per committed value. Okay, but if all of the values you're committing are small, say between 0 and something like a million or whatever, even this 20 field operations per value can go lower. And yeah, so roughly speaking, like the way I think of it is like Pippingers, saves a log n, factor, which I'll call about 20 or so over naive MSMs. Okay, and then if you're only committing to small values rather than like random values, that's another like 10x speed up in commitment time compared to if you're committing to random values or something. Okay. And so, we're talking, if you put these two things together, like Pippingers versus naive MSMs, and then small values versus random values, together it's a 2 order of magnitude speed up. It's 100x speed up for commitment time. So that's like night and day, So these are the two issues to be aware of, and like a lot of the developments in SNARK design over the last couple years have been exploiting, these sorts of significant differences in commitment time to speed up the SNARK provers. Okay, so that's Pedersen vector commitments and kind of everything to know about their computational complexity. Any questions? Great. Okay, then let us talk about polynomial commitments. Okay, so here, let's say like the committer or the prover, knows let's call it a size n polynomial it wants to commit to. I guess I'll call it Q. Okay, so most snarks, like these committed polynomials, will either be univariate or multilinear. So in the univariate case, by size n, what I mean is really like degree n minus 1. So it's like, C0 plus C1 times x plus C2 times x squared up to Cn minus 1 times x to the n minus 1. A size n multilinear polynomial would be in log base 2 of n variables. Right. So like, a multilinear polynomial in 20 variables is of size, 2 to the 20, which is about a million. Meaning if I were to list like all of the multilinear Lagrange coefficients of this polynomial, it would be a million of them, right? So like, and so typically univariate polynomials in SNARK design, if it's univariate, the coefficients people think about are in the standard binomial basis, like I wrote here. And for multilinear, the coefficients are typically in what I call the Lagrange basis, which means like the quote coefficients are actually, Q of X evaluations as X ranges over the hypercube. Those would be the what I call the coefficients, but they're really evaluations, so I call them coefficients in the multilinear Lagrange basis. Okay, so what the prover wants to commit to is either this univariate Q or this multilinear Q, and then after it sends the commitment, the verifier is going to ask for an evaluation of Q at some point, and in most SNARK applications, this R will typically be random. And then the prover has to provide the requested evaluation as well as a proof that the provided evaluation, I don't know, let me call it little v, indeed equals the committed polynomial at the requested point. Okay, so that's a polynomial commitment scheme. Okay, now Hyrax, as well as others, exploits a fact about polynomial evaluations. And this fact is easiest to see in the univariate case, but it holds for the multilinear case as well. Okay, so I'm going to state this fact in like kind of a vague way that you might not immediately understand, and then I'll explain in detail what it means. So polynomial evaluation queries have multiplicative structure. All right. So what do I mean by that? Again, it's easiest to see in the univariate case. So let's say, let's just give an example. Let's see, I want the degree to be a perfect square. So let's go with 9. So let's say Q of X is, let's say 2 plus 3X plus 4X squared up to, well, what would it be? So 0 goes to 2. So up to, I guess, 10 times X to the 8. So what I'm going to do is I'm going to write out the coefficients of this polynomial. Is it 10 or? Okay, well, we'll see how it goes. I'm going to write out the coefficient of this polynomial as a square. Okay, so a 3 by 3 square, because there are 9 coefficients. And so here I'm going to write them out: 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and here's the facts. So I can write, if I want to know Q of R, that's 2 plus 3R plus 4R squared plus, 10R to the 8th. I can actually write that as a vector matrix vector product, where the matrix is this square matrix here. Okay, and so I can actually write that as, let's see, I would want R to the 0, R to the 1, R to the 2 here. So that's the right vector, and then the left vector should be, again, R to the 0. Then it'd be, I guess, R to the 2, R to the 6. I think that should be right. So this is something I guess you can confirm as an exercise. Maybe it's worth doing for this example. So if I just look at the first matrix vector multiplication, we'd be looking at 2 times R to the 0 plus 3 times R to the 1 plus 4 times R to the 2 would be sort of the first entry. The next entry would be 5 times R to the 0 plus 6 times R to the 1 plus 7 times R to the 2, and then 8 times R to the 0 plus 9 times R to the 1 plus 10 times R to the 2. Okay, so that's like the result of just one of the two products here, matrix times the right vector. And then when you multiply that result by the left vector, everything in this first entry gets multiplied by R to the 0. Everything in this second entry gets multiplied by R cubed, and everything in the third entry gets multiplied by R to the 6th. And that sort of works out to exactly what we want, so that as you can see, so R to the 0 is just 1, right? So this just turns into 2 plus 3R plus 4R squared, which is exactly what we had here. And then, this turns into, I can't read my own handwriting. That was R to the 0. Yeah. So this turns into, 5R cubed plus, 6R to the 4th plus, 7R to the 5th, which was, the next three coefficients, and then similarly this turns into the last three coefficients. 8 times r to the 6th plus 9 times r to the 7th plus 10 times r to the 8th. So yeah, hopefully it's clear what's going on. This sort of we're kind of breaking the n coefficients into blocks of size root n, and the first multiplication kind of gives you the right powers within a block, and then the second multiplication sort of tells you which of the blocks you're in, and what one block is one row, and that's why everything works out. So that's what I mean by this fact, this multiplicative structure. So like, and in general, like kind of you give me any polynomial at all, not just like univariate in the monomial basis or multilinear in the Lagrange basis. In other bases as well, it's always the case, maybe I should have started with this, that Q of R is, the inner product of two vectors, say A inner product B, where, A is the coefficients of Q, and B is like the evaluations of each basis element, that if the coefficients are coefficients with respect to some basis, whether it's the standard monomial basis or the multilinear Lagrange basis or whatever, these are just the evaluations of the basis polynomials. And so what, in this univariate example here, this A is just the standard monomial coefficients, for in this univariate example above, and this B is just this vector of powers of R to the 0, R to the 1, up to R to the n-1. And this vector matrix vector structure is sort of saying, hey, this vector, it's not just some completely unstructured vector. It's very structured. It's powers of R. And in particular, this vector can be written as, what you can call a tensor product of two smaller vectors. And in this case, it's r to the 0, r cubed, r to the 6th, tensor product with r to the 0, r1, r2. So what I've covered is another way of saying that, like, if you take univariate polynomials in the standard monomial basis, and you write the evaluation of Q at R as an inner product of two vectors, this evaluation vector, this vector B, which I call the evaluation vector for R, has tensor structure to it, and that tensor structure is what lets you write the Q of R as a vector matrix vector product, and something identical holds for the multilinear Lagrange basis. There are other bases where this sort of thing does not hold. So like if you look at the univariate Lagrange basis, this multiplicative structure is not there. Yeah. So anyway, okay. So hopefully you followed that. So this fact, really important fact, this is exploited by many, but not all polynomial commitment schemes. So it's exploited by, so the curve-based schemes that exploit it are Hyrax and Dory. And, they're sort of, well, yeah, I'll leave it at that. But there are also hashing-based schemes that exploit the same fact, like Lajero and Breakdown. Okay, but there are a lot of schemes that don't exploit this fact. So polynomial commitment schemes that do not exploit this multiplicative structure in polynomial evaluation queries. Bulletproofs, Fry, KZG. Okay, and so and there are ways to take each of these, I think, and sort of do some kind of in between situation where you exploit some, you start exploiting. You take the scheme, which in its purest form doesn't exploit the structure at all, and then you sort of modify it in a way that does exploit the structure. But generally speaking, if you want the fastest possible prover, you're going to exploit the structure. So you should be exploiting the multiplicative structure. And as we'll see, it's typically, if you exploit the multiplicative structure, you get a faster prover, but like bigger proofs and a slower verifier, roughly. And so, there is a trade-off here for exploiting the structure. But if your focus is on prover time, you should be exploiting it. And, ironically, these are probably the most popular three polynomial commitment schemes today, and they don't exploit it. And this is part of, one small component of like this thesis that I have, which is like popular snarks today tend to be optimized for verifier costs and not prover costs. But prover time is the main bottleneck, for snark scalability. So we actually should be changing what we're doing to optimize more for prover costs rather than verifier costs. And in particular, with snark recursion, you can typically get the best of all worlds where, once you have a snark with a nice fast prover, but the verifier costs aren't great, you can bash down the verifier costs by composing with like a slower snark with a nicer verifier. So this little presentation here is, me trying to sort of spread that viewpoint a little further. Okay, so Hyrax, let's come to Hyrax. So Hyrax is basically just Pedersen vector commitments combined with this multiplicative structure. And that's it. And you will see what I mean in a second. Okay. So remember, so let's say the prover wants to commit to a polynomial Q. And as before, we're going to write out the coefficients of Q in a root n by root n matrix. So C0, C1 up to C, I guess, root n minus 1, C root n up to C2 root n minus 1 or whatever it is. And then finally C, the last coefficient, I guess, is Cn minus 1. Okay, and so what Hyrax will do is the commitment to this polynomial Q is just going to be a list of one Pedersen vector commitment for each column.
Excuse me, is Hyrax univariate or multivariate scheme, or
Yeah,
does it do both?
it doesn't matter. It works directly for both. For concreteness, let's say it's univariate, just because I think everyone's probably a little more comfortable and used to that. But all it's going to exploit is this vector matrix vector structure. And this structure holds, this vector matrix vector structure here, applies to univariate polynomials in the standard monomial basis and to multilinear in the Lagrange basis. So Hyrax applies directly to both as well. Let's focus on the univariate case, in which case these would be coefficients in the standard monomial basis. But yeah, I mean, everything would apply like basically unmodified in the multilinear case.
That's good. Thank you.
Yeah, thanks for the question. Other questions? Great. Okay, great. Yeah. So you look at each column and you Pedersen vector commit to each column individually. So you go down this column and commit, go down this column and commit to it. So it's a pretty big commitment, which is part of why Hyrax is not actually really popular at all today. But the commitment is square root n group elements, one per column. Okay. One nice thing about Hyrax though is you use the same commitment key for each column. Same commitment key for each column. Right. So the commitment key is only root n group elements. So that's nice. When we talk about stuff that doesn't exploit this multiplicative structure, like bulletproofs and KZG, their commitment key is linear in size, and it's exactly because they don't exploit this multiplicative structure. So so nice to have that nice small commitment key, only of size root n. on the, the downside, a downside is the commitment is big rather than being one group element, it's square root n group element. Okay. So that's the commitment. And now let's say the verifier, requests, the committed polynomial at some point R. And so, as we said before, this can be written as a vector matrix vector multiplication, where this vector is, the first root n powers of R. And this vector is the first root n powers of R to the root n. Okay. But I don't really actually care too much what the elements of these two vectors are. I just care that they're both of length root n. So let me just call this vector A and this vector B. And maybe I want to give the matrix a name, so let me call it capital M. Okay. So here is the evaluation proof for Hyrax. So evaluation proof. It's literally just the vector m times b, which is in field to the root n. Okay, that's it. All right, that's the proof. And what the verifier will do to check the proof, remember the prover committed to each column independently. So what the verifier will do is via homomorphism, it can actually on its own compute a commitment to m times b. Okay, that is the commitment to m times b is just, I guess we're using multiplicative group notation here. Let me switch to additive group notation all of a sudden. Hopefully that's not too confusing. So now I'm going to call the group an additive group. Let's call these commitments little c1 up to little c root n. So the commitment to m times b is literally just the sum over each of the commitments of bi times that commitment. Okay, so this is group sum, and this is a scalar multiplication. I guess if you don't like that, I switched because I can write this nicely as like an inner product between B and this vector of commitments. Then if you don't like that, I just switched group notation. I could write it as as product. So that now this is the same thing, just with multiplicative group notation of CI to the BI. Okay, so the point is, if I give you, since I've given the verifier a commitment to each column of the matrix, and then matrix multiplication works like just by it's like b1 times column 1, b2 times column plus b2 times column 2, plus dot 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 b root n times column root n. A commitment to m times b can be obtained by just applying homomorphism to the column wide commitments. So this is like a CI to the BI here is like a commitment to column I of the matrix times BI, right? And so m times b is just a sum over all columns I of that column times BI, right? And so I'm just applying homomorphism here. Matrix vector products are just a linear combination of columns. I have a commitment to each column, so I can get a commitment to the linear combination by taking a linear combination of the commitments. That's all that's going on. Okay, so so V gets a commitment to m times b. The proof, on its own, it gets that commitment. The proof is supposed to specify m times b. So how does the verifier check the proof? V simply checks on its own that if the prover sent y, which is claimed to be m times b, the verifier simply checks that y indeed opens that commitment. That is it. It just computes the commitment to y GI to the YI and confirms that that equals this homomorphically derived commitment, which in product notation is just this. Yeah, so that's how the verifier checks the proof. Okay, so, in summary, on its own, the verifier via homomorphism can get a commitment to the real M times B. Then the prover sends a vector claimed to be M times B. And to check the proof, the verifier is just going to confirm that indeed the vector the prover sends is the vector inside the commitment it homomorphically computed. Okay, and then once the verifier is convinced of that, then then it knows that then Q of R is just A times this vector Y, and that's it. So the verifier on its own, given this vector Y, can compute Q of R. So that's Hyrax. Okay. Any questions about that?
If can you hear me?
Yep.
If the number of if the length of the vector isn't perfect square, do we just pad it with zeros?
Yeah, that's right. Yeah, you would just pad it to zeros is the easiest way to do it. And that's another nice thing about zeros being free to commit to with these curve-based commitments is you can just pad things and it doesn't actually increase the commitment time at all. Literally, no increase. So that's a very natural thing to do in this context. Yeah, because
another one is this scheme is hard and anyhow, since each verifier can commit instead of prover, then it looks like it kind of knows everything.
So I didn't get so this commitment scheme is like very not zero knowledge. If that I didn't hear the whole question, but yeah, there's quite a lot of information leaked about the committed polynomial M here because the evaluation proof is pretty big. It's a length root n vector. That and each entry of that vector is like some information about M. So the book actually describes a zero knowledge variant of this, but again, my preference is to not worry about zero knowledge, just worry about succinctness. Make the proof really fast and make the verifier cost decently low, sublinear at least, and you can make things zero knowledge later, one way or another.
Yeah, that makes sense. Thank you.
Yeah, thanks for the questions. Okay, so let's briefly discuss costs. So again, the commitment cost, the time to compute the commitment, the prover did square root n MSMs, one per column, each of length square root n. Okay, which is almost the same cost as just doing one MSM of length n. Because square root n by times square root n is n. The difference is the Pippinger speed up might be smaller. Right. Remember, the Pippinger speed up is like a log factor in the size of the committed polynomial, and log of root n is 1/2 log of n. And so you might kind of lose a little bit in prover commitment time potentially, since you're committing to smaller vectors. Committing to many smaller vectors might be a little slower than committing to one giant vector. On the other hand, it turns out that if the values you're committing to are themselves small enough, you don't even lose that. So anyway, so it's square root n MSMs, each of length square root n, but and that's pretty close in cost to just one MSM of length n, up to some caveats. The commitment size, like I said, is square root n, which people don't like, but it's still sublinear. So square root n group elements, and the verifier cost, or so let's say, so Well, the evaluation proofs are square root n field elements. Okay, and the main verifier cost to check the proof is doing 2 MSMs of size root n. 2 MSMs? Yeah, I guess it is. So 1 MSM is to take the linear combination of the commitments, and the other is when the prover sends y, which is claimed to open that linear combination of commitments, to then kind of recommit to y and confirm that it thereby confirm it indeed opens that commitment. So again, there's one linear combination of one MSM of size root n to homomorphically combine the column commitments, and then another when the prover gives the opening of that to confirm it's a valid opening. So this is the main verifier time cost, and in total, it's like square root n verifier cost, right? It's like square root n proof size, square root n like time to check the opening proof roughly, and that's Hirax. Okay. And so, it's not super popular because people don't like the square root n verifier costs, but it does have some nice properties that, I'm covering it out because it's simple, not because, I think it should be the most popular commitment scheme out there. But it does have some nice properties. I mentioned that the commitment key is size only square root n. Whereas, like stuff that doesn't exploit this multiplicative structure in evaluation queries, and uses groups has size n commitment keys. And another nice thing is the prover, so the let's say the evaluation proofs are super fast to compute. Right. So as we'll see when we cover bullet proofs, the evaluation proofs there involve the prover doing a ton of scalar multiplications, a ton of group work. Here, the evaluation proofs involve no group work at all, right? Literally, the evaluation proof was just multiply this matrix by this vector. And in fact, simply evaluating the the polynomial at the point R is going to require doing that matrix vector multiplication anyway, right? Like probably the way the prover is going to evaluate Q of R is to do something that looks like this, A times M times B anyway. So you could almost call these evaluation proofs like free for the prover. I think it's kind of fair to call them free. Like the prover does no extra work on top of just evaluate the committed polynomial at the requested point. So these are the good things about Hirax. The bad things are the square root verifier costs. So yeah, if one day we got like super duper duper good at recursion or something, then maybe the square root n verifier costs would be irrelevant essentially, and these benefits would win the day, and Hirax would become really popular or something like that. And it's also transparent. That's something that's nice. There's no trusted setup. The commitment key is just random group elements. Okay. Now, I guess I should say a little bit about a security proof. Maybe. Yeah. So, let me think if I want to say this or not. Okay. So I think it's very easy to establish that Hirax is secure, meaning like given any prover that can produce convincing evaluation proofs, one can actually identify a polynomial Q like inside the commitment that has the same evaluations that the successful evaluation proofs correspond to. It's pretty easy to show that if the prover actually were to prove. So Hirax doesn't require this, but let's say we required the prover to prove it can open each column commitment. Okay, if we did that, that would add, noticeable extra cost to the commitment scheme. So we don't actually have to do that, and we won't. But let's say we did that. So if the prover proved it knew how to open each column commitment, then in your security analysis, you can literally like imagine there is a vector inside each of these commitments, right? And then, you know, then everything becomes very simple, right? Because, you know, if you take those vectors and, you know, you look at the matrix whose columns are those vectors and call that matrix M, you know, then everything just works out where indeed, you know, you've established that Y is M times B, and you know, and that then the verifier is getting the correct evaluation, which is that Q of R is A times Y. So the security proof kind of goes, you know, completely straightforwardly, you know, from, you know, the binding properties of Pedersen vector commitments. If the prover actually proves it knows how to open every one of the Pedersen vector commitments it sends as part of the Hyrax commitment scheme. Okay. Now in Hyrax, we don't actually require the prover to prove it knows how to open these column commitments. And so that actually can create some attacks, but those attacks only exist. So if we don't make P prove it knows how to open each of the column commitments, like this commitment scheme, like would be attackable. It's actually not secure at all if the prover can choose the evaluation point itself, like adversarially. Okay, and what would the attack be? It would be like, it would be the following, like, you know, the prover would be saying, hey, you know, before I determine the commitment, I'm actually going to, you know, choose in advance what the evaluation point will be. So the attacker, you know, is going to choose R in advance before it sends the commitment. It would then, I want to say this. See, I'm going to try to sort of invent the attack on the fly. So that, you know, R turns into these two vectors A and B, and if the prover is honest, you know, there's like this matrix M it's going to commit to column by column, but this is an attacker. So once it chooses R, it knows what A and B will be. Okay, and now, what would you do? So you know, let's imagine for simplicity, let's just focus on, oops. Let's just focus on like the 2x2 case. So basically what the attacker is going to do is it's going to pick two group elements like C1 and C2, and it's not going to know how to open those commitments. Okay. And so it will choose C1 and C2 so that like, so you know, now there's just B1 and B2, B1 and B2 and A1 and A2. Everything's just length 2. So it will choose the commitments so that, you know, what the verifier winds up looking at, is, what is it, B1 times C1 plus B2 times C2. And what the prover will do is it will just, so let's call this C3. So let me define C3 to be this. And so it will make sure that it can, so the attacker will sort of ensure it can open C3, but not C1 and C2 individually. Okay, and because, you know, Hyrax only checks that the attacker can open C3. You know, this combination, this linear combination of the column commitments C1 and C2. And so the attacker can, you know, pass the verifier's checks so long as it can open C3. Okay, but if the attacker didn't separately establish that it knew how to open C1 and C2, the ability to open C3 does not imply the ability to open C1 and C2. So in this situation, like they're actually, if the attacker can't open C1 and C2, then like there is no, like matrix of coefficients, in the attacker's head. Right. So there is no committed polynomial that the attacker is like, actually answering the evaluation query consistent with or anything like that. It's just, it's sort of fixed this one this one evaluation and claim and is able to answer that one claim, and that's it. It can't kind of do anything else whatsoever. Whereas if it had to prove that it knew how to open C1 and C2, then the fact that it knows how to open C1 and C2 like gives you the coefficients in these columns that then give you the polynomial that it's actually evaluating here. Okay, so that is an attack that is there. It's a working attack. If you don't make the Hyrax prover prove that it knows how to open each column commitment individually, and the attacker can choose the evaluation point. But fortunately, in SNARK design, when we apply these polynomial commitment schemes in SNARKs, like this evaluation point R is chosen by the verifier, not the attacker. And then, that's in the interactive case. And then with Fiat Shamir, to make it non-interactive, this R is chosen by Fiat Shamir hashing, other stuff. And either way, what that basically means is R is not in control of the attacker. Right, the security proofs are actually fine to basically model R as R is just a random, evaluation point. And the key point is not known to the SNARK prover when the polynomial is committed. When Hyrax commit is called. Okay, and you can actually show that in this setting where R is chosen at random, and it's in particular not known to the SNARK prover when committing, you can actually show that Hyrax is secure. You can actually extract the polynomial out of the prover's head efficiently, even if these the prover does not prove it knows how to open each column commitment. And the way you do it, and I'm not sure that I've seen this written down anywhere, so I should update the book at some point. But the way you do it in this case is you basically just run the prover on like square root n different like eval points, each chosen at random. Okay, and so it's going to give you, like m times b for b corresponding to each of these root n different b's, assuming it succeeds. It successfully produces an evaluation proof for each evaluation point. So you're going to like run the prover once and then like rewind it and run it again with like a different evaluation point, and rerun it and run it again with a different evaluation point. And if it succeeds root n times, and moreover these vectors b are linearly independent, which in the univariate case I think they're guaranteed to be if the evaluation points are different, then you can actually you just get a system of like square root n equalities in the square root n, in the n unknowns of m, and you just get a linear system that you can solve. So that is, given m times b for square root n different linearly independent b's, you can just solve for m. Okay, and so that's how you would establish security of Hyrax in the context of the prover getting posed like random evaluation queries, and in particular the evaluation points not being known at commit time. And that lets you not pay the cost of the prover establishing that it knows how to open each column commitment, explicitly. You get security anyway. Okay, so that is a little bit about security of Hyrax. Let me pause. Any questions?
The attack you described, would it be correct to call it to call it the situation when approver controls the proven key?
I'd say if the prover controls the proving key, the issue is going to be that the commitment scheme is just not binding at all. And so it can sort of open any commitment to anything at once. In particular, if I like know a discrete, like if I know an x such that gi to the x equals gj, it's pretty easy to come up with like multiple openings of any given commitment, and that's where this security analysis is going to break down. Does that make sense?
Yeah, now I see the difference, and it raises the follow-up question. In this transparent setting, how do they get this proven key? Is it kind of Diffie-Hellman thing?
Yeah, it's actually just they're just random group elements, and so they're really just obtained by evaluating a PRG many times, and there are some annoying details which I believe are solved with what's called hash to curve. Basically, hash to curve. By the way, there's a chance I'm embarrassing myself and I'm wrong about this. This is sort of more in the implementation details than I sometimes go. Um, this is a way. This is basically a way of generating random group elements, or basically turning random strings that come out of a PRG, like random numbers, if you will, into random group elements. Um, and I don't know all the details, but the idea is that I think the rough idea is, like what is a group element on these elliptic curve groups? Well, it's actually a pair of field elements satisfying some equality, like y cubed equals ax plus I don't even remember. And so it's just the output of a PRG is just like uniform random strings or numbers or something, and it's not completely trivial to turn uniform random numbers into random pairs XY satisfying this equality. But hash to curve gives a way to do it. And roughly, I think the rough idea would be that you take a generator of the group and you take your random number that comes out of the PRG and you treat it as like a random exponent. So if that random number is R, you like look at G to the R and you like hope that that's a random curve element. But there must be some problems with what I wrote, what I said verbatim. Maybe I don't know if they're just coming in because the group isn't necessarily a power of two size or something. And so you do something a little more complicated and smarter. And anyway, but the gist is the commitment key in the transparent setting is just a bunch of random group elements, and there's kind of a way to take a cryptographic PRG and turn it into what essentially random group elements, and that's the commitment key. Does that make sense?
Yes, and hence this is part of Fiat-Shamir, is it?
Part of what?
Fiat-Shamir transformation.
Oh, I don't think I'd call it Fiat Shamir. No, Fiat Shamir is like if you have an interactive protocol and you don't like the interaction, how do you cut out the verifier challenges and kind of have the prover choose them on its own? And the answer there is hash the previous messages. Here, we're using a PRG instead of just hashing. So I think it's a little different.
I mean, if we don't want prover to control the proven key so that he couldn't make another kind of attack, then how do they come up with the proven key with the verifier?
Yeah,
when
so
you don't have.
it's like the proving key is established as follows. So it's like take this standardized PRG that like NIST standardized, and if I want to come up with like square root n random group elements, like roughly what I do is I evaluate the PRG. Like I pick a so let's call the PRG uh, little h. I don't know. That's our PRG, and NIST standard declared this to be the PRG everyone in the world is going to use. I do not ask me for the name of any of these PRGs. I couldn't tell you. And then we all agree on a seed. Say I don't know the first sentence of Hamlet. Okay, and then the square root n group elements are just the PRG evaluated at this seed, comma I, as I ranges from 1 to root n or something. And so this spits out like square root n random values. And then there's some hash to curve technique to turn those square root n random values into random group elements. That's my own mental model of how these transparent curve based commitment keys are generated. And I've never looked deeper than this, so there could be some small details I'm getting wrong. But this,
Yeah,
yeah,
that makes sense. I now remember this, and I kind of never thought that they turn out to be quite stable.
yeah, and
It's a thing that I should incorporate in my mental model. Thank you very much.
yeah, sounds good. Yeah, and yeah, one nice thing is like you do this once for all time. It only depends. And you're good. You're good forever, regardless of what you want to prove or commit to or what have you. Um, Up to inputs of size root n, or n or whatever. Hyrax needs a root n size community key to commit to a polynomial of size n. So and actually you run into the following situation annoyingly often, which is this sort of key generation procedure is done once forever. Now, when you do it, it's a little bit expensive because evaluating these PRG square root n times is like, not nothing. So if you actually like benchmark a snark that uses, Hyrax or bulletproofs or something, probably the implementation is actually going to generate the commitment key from scratch every time, just because no engineer has come and bothered to like do it once and store it for all future runs of the program, right? And so you actually wind up with like this key generation, if you do it like on the fly, is more expensive than the rest of the snark. And so you wind up with some messed up benchmarks where people are really just measuring the time to generate the commitment key and like attributing that to the snark prover, and that's like the dominant cost, when really this would be done once forever, and like you shouldn't actually count it towards prover time. So no, these details about how this key is generated and like what's actually going on are like important to be aware of, if for no other reason than to kind of not come up with the wrong timings in benchmarks or something. Okay, other questions? All right, so I think we'll wrap up here today. I guess I'll just tell you very quickly, like bulletproofs. The what are the pros, and we're going to discuss it next time. What are the pros and cons compared to Hyrax? Maybe I'll start with the cons. So, like I said before, it's a linear size commitment key. It's also very slow opening proof computation or evaluation proof. Okay, and it's also very slow evaluation proof verification. So those are all the downsides. The plus sides are the commitment key. The commitment is just one group element. not root n. And the proof size, the evaluation proof size, is log n group elements. So much smaller than root n. Okay, so it's slow verification of the proofs, but the proofs are small. Small proofs, slow verifier. That's not a common combination. Normally, small proofs go hand in hand with a fast verifier, but not for bullet proofs. And like Hyrax, it's transparent. So I'd say those are the pros and cons. Typically, so bulletproofs is in deployments, maybe most prominently in Zcash now, and I think in Monero too. And they care about proof size, I guess, a lot. They're also able to mitigate some of the slowness here with some kind of amortization techniques. And so, the short proofs win out over the slowness, the slowness of generating those proofs and of verifying those proofs compared to Hyrax. So people do use bullet proofs. They don't really use Hyrax right now. And so probably you'll all be more interested to learn about bullet proofs than Hyrax, but Hyrax is much simpler. So we started with Hyrax. So we'll see this next time. That's everything for today. So thanks as always. Any last questions? All right, we'll call it a week then. Thanks, everyone. See you next week. Yep. Bye.
Thanks a lot.